So these are the two kinematic equations that most of you have really wanted to use so far this quarter. And we'll introduce them now and you can use them, but you have to know when you can and can't use them. This one we think is a general term for displacement, but it's not. It's only for constant acceleration. The general term for displacement is where you are at some time is where you started plus the integral of the velocity, or the area underneath the velocity time graph. So where do we get this? If we have constant acceleration, only if we have constant acceleration, then this is a straight line with a slope of a, the acceleration, and this is a right triangle. And then this area is just v naught t, which is this, and this is a triangle, 1/2 a times t times t. Or you could just say, look, the velocity is equal to v naught plus the integral of the acceleration, which is v is equal to v naught plus acceleration times time. And then we integrate that, and we would get v naught t plus acceleration times time squared over 2. Okay, so you can go ahead and use this equation now and feel good about it, but remember, it's only for constant acceleration. Acceleration can change, but it's great for stuff like falling in a gravitational field, for instance, of negative 9.81 meters per second squared. Now this equation, this is a troublesome one, because it can only be used for one dimension. Don't start adding velocity in one direction and velocity in another. It also loses sign, because you don't know if the final or initial velocity is positive or negative. But where did this come from? This came from looking at this equation and wishing we could get rid of time. Well, how can we get rid of time? We can solve for time here. Time is equal to v minus v naught divided by the acceleration. So if you take this and slam it into this equation, you'll wind up with this equation. I'm sure they do that very nicely in your textbook. Check it out. There's really only two kinds of physics questions I can ask you about this formula, and it'll come in handy. This one, never. Forget it, it's just trouble. This is utilized for the classic physics question of, does the cop catch you, or when does the cop catch you speeding? I imagine I'm speeding. I'm going some speed vp. So my displacement is equal to some x naught plus vt. I'm just speeding down the road and I pass a cop, and in a moment he starts up and begins accelerating. So his displacement looks like this. But I've got to jump on him and I'm moving very fast. He's not moving at all in the beginning. So we say at t equals 0, let's say, the t equals 0 would be when he gets started. So I'm already, so many meters ahead of him, and I've got some crazy high velocity that I'm moving forward in time. Now, the policeman begins at 0 meters per second. So his line is flat, but he's got acceleration, so this curves up parabolically. And here he busts my ass. Right there, stops me. And I can find out exactly where I am. How? The key physics is, at this point, he and I have the same displacement. So you take my displacement as a function of time, x of Pete is x naught Pete times vpt, and you set it equal to his displacement as a function of time, and you can find time and then substitute it back. Of course, it's more interesting if you're trying to catch the policeman, because there might be the opportunity you miss him. What if you're speeding along and the policeman starts ahead of you? Now, you do the same thing, except he has the initial displacement and not me. Because you might actually pass him and then he passes you back because he's accelerating, right? Kind of like this. In which case you'd have two roots to this quadratic equation. You know, the radical b squared minus 4ac would be positive and you'd have a plus and minus, right? Or that radical would be 0 and you would just touch him and then he'd move away. Kind of like this. Vroom, vroom, right? Or, too bad for you, you never reach the cop because he accelerates too fast for you. And then this would be a negative number and you'd have an imaginary time. The other scenario that uses equations is projectile motion problems. Because we know gravity accelerates only in the y direction. The force of gravity is only in the y direction, and so your acceleration in the x direction due to gravity is 0. Let's say we shoot off a cannonball, so that once it takes off, there's no longer any force except the force of gravity acting on it. So it has some speed v0 and some angle, and we can separate its velocity into a v0 in the y and a v0 in the x. So what happens after that? There's only gravity acting on it, so the acceleration in the y direction is gravity, but the acceleration in the x direction is 0. And so it just moves along constantly at that same speed, and we can say that x is equal to where it is at any time is equal to where it started plus time times the x component of velocity here. Now in the y direction, we have the full-blown displacement formula with constant acceleration. And so its height at any given time is where it started, plus the y component of the initial velocity, plus this acceleration term of gravity always pulling it down. So you find its displacement in the y direction goes up and down. And in the x direction, it just moves along at constant velocity. And you add those together, and you get a trajectory that looks like this, and a velocity at any given time that has the same x component, but a smaller y component, and then a larger y component in the other direction. And what you know, when it hits the ground, it's moved some distance x in this direction, and some distance y in this direction. And what links these two? Well, it's moving forward for the same amount of time that it's moving up and down. So these are coupled equations in x and y, where y tells its elevation and x tells its horizontal displacement, and they both rely on time. So remember, your vertical time, how long you're in the air going up and down, is the same amount of time as you're moving forward at this constant velocity. Please check out section 3.4 in your text. And you might want to read section 3.1, 3.2, 3.3 if you think you need the review.